Good morning, dear colleagues. We are starting our first plenary section today. Let me introduce the first speaker. This is Professor of Physics Department at Loughborough University, brilliant specialist in nonlinear dynamics, quantum chaos, and quantum computing, Professor Alexander Balanov. His talk is devoted to chaos and hyperchaos in the chain of quantum coherent elements. You are welcome, Alexander.
Thank you for introducing me. First of all, I would like to thank organizers for giving me an opportunity to report our results in this conference. And it's a double pleasure for me because this is a joint results. Actually, this is a collaboration between 3 universities, which I will mention later on. So it's going to be about the chaos and hyperchaos, very complicated dynamical regimes in a chain of quantum coherent elements. And quantum coherent elements are going to be, in this case, Rydberg atoms. So I deliberately decided to touch a little bit about these topics because it's at the moment it's cutting edge in solid state. And I would say it's in quantum solid state, quantum information physics. And also this is exactly what our result about, together with some other quantum coherent elements like some superconducting qubits. This is a brief content of my talk today. So in fact, it's logically has 3 parts, answering the questions, where is Loughborough University, what are Rydberg atoms, and what we are doing with those Rydberg atoms. So the first part is rather anticipation to answer of probably one of the most frequently asked questions, which I have on different kind of conferences and meetings. As I said, this is a result of collaborative work between 3 universities, Loughborough University in the UK. And here I would like to note Professor Zagoskin, who led quantum part of this research, Mark Greenaway, who is also expert in quantum physics and transport in quantum system. It's a big pleasure to also acknowledge, I think, leading contributing roles from group of Professor Kramov. I especially would like to mention very talented young researchers, Vladimir Makarov and Andrei Andreev, who done major contribution and numerical simulations of our results. I also would like to mention Professor Frumhold and Professor Wei-Bin Li from Nottingham University, who are actually experts in Rydberg systems. So where's the Loughborough University? So this, as I said, this is probably one of the most frequently asked questions on the conferences. So, and to find Loughborough University is very easy. So if you look at the map of the UK and cut off the Scotland and put your finger in the middle of what is the rest, you very probably cover Loughborough. So Loughborough has 2 campuses. One campus is in East Midlands and another campus in London. And Loughborough itself located between Leicester and Nottingham as a reference points. It's 12 miles north from the Leicester and 18 miles south from the Nottingham. This is a photograph of Loughborough University campus made from copter. In fact, this is only part of the campus, and this is a physics building as it looks from the side of the birth view. If you look on the campus from other side, it's still not complete campus. So you see, it's even drone is not enough just to have a look on entire Loughborough University. It's the longest single site campus in Europe. So, and from this perspective, physics and chemistry building we shared with chemistry is located here. So as you see, we have a lot of sport facilities, a very long university, which is constrained from the side by residential area. So what Loughborough University is famous, at least in the UK. So this is a top 10 university in all national leagues. This year it's top 7, if you would like to be more precise. This is best sporting university in the world according to QS rating. So essentially we're #1 in the sports sciences and sport-related technologies. One of the 5 universities, British universities, who got any #1 in any categories of subjects of science. So we among such grants like Oxford, Cambridge, Bristol, and Imperial College. We top 10 research university in England, and we awarded gold for teaching excellence. So to summarize, so this is middle-sized British university. So it occupies about 440 acres. It's 120 hectares, if I'm not mistaken. So we have around 20,000 students and around 4,000 staff, including technicians. So to summarize, this is internationally most invisible of top British universities. So if you ask somebody to list or to pronounce any names of any top 10 British university, I don't think anybody from outside the UK would probably mention Loughborough, with small exception. And that's why I decided to start my talk with these facts, just to make Loughborough a little bit more internationally visible, if you allow me. So Department of Physics, what I belong to, it consists of 19 faculty staff. This is permanent staff and not counted postdocs. So we have 250 undergraduate students and 34 postgraduate students in the department currently. So our research interest belongs to a wide range of solid state physics and related physical subjects. It includes some major research topics include quantum and nanoengineering and design, high frequency solid state physics and electronics, novel materials, including functional materials, spintronic materials, different kind of exotic topological materials, for energy harvesting, for new generation of devices and electronics, physics in complexity. This is interdisciplinary area of our research, which covers biophysics, theory of networks, nonlinear dynamics, devices for unconventional computing, including quantum computing, neuromorphic computing, analog computing, and also cognition modeling. So this is the scope of our research. So Rydberg atoms going to be my subject today. So what are Rydberg atoms? So if you look on a model, usual model of atom, as Bohr at least imagined it for himself, it's not quite correct because orbits might be quite complicated, but it's quite simplified model, which allows us to grasp the concept. So the atom, we look on the atom as a subject which consists of nuclei and electrons, which are rotating about positively charged nuclei. And we understand and we know that electrons rotate only on specific orbits. They're not rotate on arbitrary orbits. And these orbits actually specified by a certain kind of energy. And the electron may change the orbit only by having certain portion of energy. So as I said, orbits cannot be really arbitrary. And this is because of quantum mechanical slope. So only certain quantum of energy would allow the electron to change orbit and be on the higher energy orbit far away from the nucleus. So this is usual atom. And what is Rydberg atom? Rydberg atom, this is atom whose outmost electrons is highly excited. So in fact, by certain perturbation, for example, by a light from the laser, it's consume huge amount of energy and change orbit, being far away from the nucleus, and therefore actually having weaker coupling with the nuclei, weaker bonding, if to be specific in terms of right terms to use. So this makes this atom very have very interesting properties. First of all, these electrons are really far away from nuclei. So essentially it means that the quantum number corresponds to this electron might be very high. So if we associate, for example, the lower orbit as a quantum number 1, the highly excited electron may have quantum number 100, for example, really far away from the nucleus. And therefore bonding between nuclear and electron is weaker. And essentially it means that this electron becomes really sensitive to any change in environment. And when I'm saying change in environment, I mean, for example, effect of field. So any presence of field may affect the orbit and correspondingly the electrical properties of this atom. So the proximity of this or electrons to another atoms may create some chemical bonds. This is also sensitivity to the matter, which is close to this atom. And also it's quite interesting, when the atom, Rydberg atom, has an electron far away from the nucleus, independent what kind of atom it starts to behave like a hydrogen. So this is because the electrons which are close to the nucleus screens the influence of the nucleus to far moving electrons. And in fact, it's this atom may be considered as an atom with a certain kind of big nucleus and just one electron, exactly like a hydrogen. And in fact, the spectrum of, of such atoms is going to be very close to the hydrogen spectrum and are based to Rydberg's law. To summarize, so the Rydberg atoms creates very interesting playground for studying quantum mechanical phenomena. So because we have a separated orbit quite far away from nuclei, and this orbit is very sensitive to any kind of probing fields or any kind of interactions with other fields or with other atoms. But it also becomes a very interesting subject for different promising applications. So what those applications might be, I will tell you a little bit later. But first, let's consider how do they prepare the Rydberg atoms, how they cook them, how they made them for future applications and studies. So there are different ways how to do it. Probably one traditional and well established and also historically the first is using magneto-optical traps. So essentially this is a cooling system, but not just a cooling system when we create around low temperature environment and then trying to bring this atom to low energy levels. It includes some active components, and this active components is a laser light. So in fact, they create trap for the different kind of atoms. Usually they put this in a vacuum chamber, and the gas they use is very dilute. And then they using the crossed and contra-propagating laser light to be able to affect by laser pulse, by laser light to each atom. What does it do? It's decrease kinetic energy of this atom. Essentially meaning that they decrease their temperature of the clouds of this atom further down. And in fact, they kind of stops them. They slow down the motion, they drop the temperature, and they form what they call Bose-Einstein condensate. It's not subject matter today, but it is a very condensed superatom state if it's not fermionic matters, which behave like one single atom. To make further constraint, they apply a magnetic field, and magnetic field is applied by two coils. This is a coils with a current which is propagating in opposite direction. That's create additional three-dimensional potential with a potential minimum just inside of this chamber. So they have kind of two components here. First, they create optical potential, bringing atoms towards the lower quantum states. And further down, they try to keep this atom inside a certain space. Of course, the particles, the atoms with high kinetic energy may escape that, but it's even good because what is left would be really close to the ground state, the lowest energy possible of those atoms. So once they trapped and cooled down the dilute gas of those atoms, ions, so they may apply a further perturbation, bringing the outmost electron to the higher state. That should be really precisely counted wavelengths of the laser, which makes one valent electron travel to the higher energy orbit. So this is a very simplified explanation how the trap work. And this is the heart of all the different recipe how to prepare Rydberg atom systems. That might be done in a more sophisticated way. This is one of the setup, which is given in this quite recent Anderson work. The particular property of this setup, that's create very stable and very efficient way to create Rydberg atoms. In fact, it's again creates some laser system. I'm not going to pay attention to the optics. It's different kind of focusing. Important part, well, there is a magneto-optical trap here. There is a certain additional stimuli which change polarization of the light in the laser. And there is some camera which is indicating luminescence from the Rydberg clouds. So what does MOT do, magneto-optical trap, as I said? It's actually traps some atom in some quantum well, and this quantum well now optical. If you would like to have a Rydberg atom, you need to excite this atom. And excitation means that atom should climb upper to this quantum well. And they also suggest that instead of making the climbing by few laser pulses, which is not reliable and the efficiency is not very well, they change the polarization of the light, creating this optical potential. And what they do, they flip potential well and potential top. So, and as a result, the Rydberg atom previously lying on the bottom of this potential well climb on the top closer to the Rydberg state. So in fact, by flipping this, they make it the atom be easy excitable to Rydberg state. And therefore efficiency of such setup is a quite high. This is one of the traditional at the moment way how to create Rydberg atoms cloud in the magneto-optical trap. In fact, at the moment, there are possibilities and technology which allows you to create some lattices of Rydberg atoms. So for this aim, they involve holographic microtrap. The idea behind that is the same, but now it's not just a simple laser light. It's not just a simple harmonic or plane wave, or not planes, polarized circular polarized wave, but now they applying certain kind of target. And this target, depending what is they would like to create, producing some holographic image on the slim, which is where they projected this is a laser light. This holographic image create optical potential wells in a certain space or in certain position in the space. So in fact, by having different targets and involving the holographic method, they may create the potential well forming, for example, this grill, or it might be circle potential well, or it might be something sophisticated like this, for example, or it's something mimicking the crystallic two-dimensional crystallic structures. So this is the result of the measurements of the luminescence from Rydberg atoms. So, and you can see they indeed were able, depending on what target they applied, they were able to create different configuration of Rydberg atoms. And in fact, induce different couplings between Rydberg atoms trapped in each potential wells, which is corresponds to this dot on this image. This is a simple explanation, but very complicated setup, because in principle, they're using special holographic algorithms to optimize the image, holographic image, which would create such a traps. So they actually looking at the feedback, they checking luminescence, and depending on what is the current output, they change, in fact, the picture of the target to make the hologram in such a way when the luminescence from all of the potential well will be of the same intensity. So this is a very complicated device, but it works. And what is most important, it may create different kind of spatial configuration of Rydberg atoms. This is about recipe. So what about the application? You see, at least I will try to explain you that the nature of Rydberg atoms, they highly sensitivity to the probes, fields, and matters around, allows quite efficient manipulations of this object. And there are a few applications involving quantum technology at the moment very of great research interest. And among them, you can imagine it might be quantum computing, sensing, and some exotic things, which is called quantum chemistry or quantum synthesis of the new quantum molecules. About sensing, for example, this is one of the scheme in which Rydberg atoms might be used for sensing. And the results of these measurements returned quite impressive sensitivity, both in terms of sensitivity to the frequency of the electromagnetic waves and the field sensitivity, amplitude sensitivity. So the sensitivity of the spectra returns 30 microvolts per centimeter per square root of hertz, and it's possible to sense, to detect the electric fields of a strength of microvolt per centimeter, which is quite impressive. For this aim, they employ quite interesting phenomena. So this is electromagnetically induced transparency. By the way, first predicted in Gorky, Institute of Applied Physics, now Nizhny Novgorod. And it's actually the effect itself is in the following. So if we have certain kind of system, quantum system, having 3 levels, and this 3-level system would might correspond to a certain substance or to a certain set of resonators. It depends on what you're exploiting and what you're investigating. And if you apply a laser to such a system, so definitely in certain range of frequency, the laser energy will be absorbed. So there will be huge absorptions, and these absorptions, as we know, is related to the quantum transitions. For example, it may relate to the bringing electron from the lower level to the upper, or it might be vice versa, induce jump of electrons from the higher position to the lower. All this requires energy, and all this consumes, in fact, photons from the laser. However, it was predicted that if we carefully tune of 2 lasers, and one laser can probe laser of small intensity, and another one is a coupling laser with a larger intensity. For example, in this 3-level system, all this line corresponds to the energy level of certain substance or of certain electromagnetic device. And this is lower, middle, and higher level. So if we simultaneously put 2 lasers, we can create a picture when we will actually elevates atoms for the lower quantum energy level to the middle one and drops a higher atom from higher level to the lower one. And under certain condition, those 2 fields become to interfere. So they may create a situation when on average, and statistically, we will have no atom on the middle level. In this case, this substance previously absorbing the light become transparent for both frequencies. Essentially, it means that if you put detector in such a system, and a certain range of the frequency, you will have a peak, which will correspond to transmission this light through the substance under study. This peak is very narrow, and in fact will correspond to one of the transition, and this particular configuration transition an electron between these 2 levels. Especially if if we have asymmetry, so the intensity of one laser is a higher, we can actually to control which wavelengths will be more transparent. If now we introduced a certain electromagnetic perturbation, that would split the middle level. Another options, if you have in your system some another level which is unachievable previously for this light, for these lasers, one electromagnetic perturbation create the possibility to drop or to lift electrons to this layer. In this case, electromagnetic transparency will exist, but now not on the frequency of the laser, but on the frequency of certain detuning. So what does it mean in terms of observation? That instead of one peak, which corresponds, for example, to the wavelengths or frequency of the probe lasers, we will see 2 peaks around these frequencies. An appearance of 2 peaks means that there is a presence of certain electromagnetic field. So this is how, and as I said, the Rydberg atoms, they're very highly sensitive to electric fields. It's a single electrons, very far away from the atoms. So small, very small, tiny field perturbation may create effect. So essentially, if we have a rubidium vapor cell, which might be, by the way, if they prepared under room temperature, and if you all see a picture like that, we're able to detect electromagnetic wave. So this is one of the application. In other applications is quantum chemistry, it's creating new types of molecules. When, and on this graph, this is a surface plot of the radial electron density, and green dot here is an unperturbed rubidium atom, and the red one is a Rydberg rubidium atom, so with a far away outmost electron. Together, through the interaction of these electrons with the valence electrons on perturbed atom, they may create molecule whose size will be really huge. And the electron orbits in average will be really far away from the molecule itself. It's not only creates new bonding from chemistry point of view. I don't want to give some details. It's very interesting work which you can find it in this publication. But it's also create the possibility to create new chemistry, totally new chemistry. And this is at the moment one of the cutting edge in the Rydberg science. So another thing is quantum computing. Both are traditional and analog, digital or analog quantum computing, easy manipulations by Rydberg atoms with the help of the lasers, laser tweezers, and so on, creates a possibility for different logical configuration. And if you would like to have some idea about that, I will refer you to this review. This is one of the most recent review, probably the most recent review on Rydberg atom physics currently. It might be a quantum chemistry simulation, in fact, analog computer, where flipping will describe some kinetic terms in chemistry. Some additional fields will create mimic nuclear interaction, some chemical molecular, and electronic repulsions will be given by certain specific configuration in coupling between neighborhoods atoms in the optical lattice. This is optical lattice created by lasers, and this circle, these balls actually corresponds to the Rydberg atom's position. So it may create a possibility for quantum, for analog quantum simulation, for example, chemical molecules. Why do we need it? Because in chemistry, in modern chemistry, it's very important to know what is an electron energy structure, because that's a give you a possibility for both considering synthesis or certain kind of new materials and so on. We were actually motivated by the fact that despite of many and huge amount of research, very interesting research in Rydberg atoms, the far from equilibrium dynamics of Rydberg atom is not very well understood yet. And as an expert on nonlinear dynamics, that draws attention, and especially have been motivated by these two works by a group of Lee, who actually first started to consider that seriously. In fact, there are many works, but this is where they started to consider Rydberg system as an open system. So they consider specifically situation when the Rydberg atoms in the ring or in the grid, we started our consideration from the ring of Rydberg atoms, actually being on the excitement of external laser pulses, they created so-called Rabi oscillations. But in the same time, there is a dissipation. So there is a possibility for quantum coherent atom to be defaced, or simply lost its coherence, or lost its energy because of connection with an environment. And Hamiltonian for such a system is presented here. So it includes Hamiltonian energy of each particle in such a lattice, in such a ring. And that Hamiltonian for each particle creates, in fact, attributes reflect the fact that each of the Rydberg atom is under effect of the laser frequency, and also the Rabi oscillations, which appears because of laser. So this is different energy components here. And of course, all these Rydberg atoms are connected to each other, so they coupled. So what is a coupling between Rydberg atoms? There are possibility of, there are different origin which coupling, how coupling between close atom appears, but one of them is probably most prominent, and it's called a Rydberg blockade. Because this atom has an electron far away from the nucleus, it's actually demonstrate very high dipole moments. So very high dipole moments allows the atom to create certain kind of special configurations and be sensitive to the field as well. So, and essentially, implication of such large dipole moment is the fact that if you have two neighboring atoms and one atom is excited, the second atom has a very low probability to be excited, because energy, excitement of energy is scaled as a n3 or n, even n power 11, where n is a principal quantum number. Principal quantum number is associated with an orbit with a higher energy. Farther orbit has a larger n. As I said, for Rydberg atom, it's totally normal to have n being 50 or even 100. So essentially, it means that if one atom is excited, second one very unlikely be excited and be in Rydberg state. Let's create a kind of let's create analogy. If you're considering spin system, that's create what they call antiferromagnetic coupling between the spins. To consider the system open, we have to introduce dissipation, and one of the way, probably in this case is the best way to take into account dissipation, is to use a master equation terminology, master equation description, with a rho is a density matrices, but density matrix is special kind of probabilities, or better to say correlations. So it's describe correlation between all states in all atom forming the system. So, and dissipation taken out by this Lindblad operator, which takes into account both dephasing and loss of energy, and gamma characterize some certain rate of this dissipation. Such system, by the way, it's quite complicated because this matrix has a rank counting all state and all atoms. So it's quite huge matrices, and it's essentially that the dealing with these equations with a number of particles more than 100, maybe a few hundred, will require probably supercomputer. However, we started with a simplified consideration. We neglected entanglement, quantum entanglement, which give us a possibility to work only with a diagonal element of this matrix. So in fact, we say that every element of matrix can be factorized. So this is how its factorization happens. And if we're using these factorizations and neglect any kind of entanglement, even two atoms entanglement, we will come to the very nice set of equations, classical equations, if you wish, where variable omega and q describe inverse population. Inverse populations, what is a fraction of atoms in Rydberg states, and coherence, which characterize indeed closeness of the atom to the coherent state, to the state when the phase is preserved. So in fact, we have now the chain of such elements in the system, and we would like to investigate the solutions of such equations, which are as time tends to infinity, so the limiting sets of this solution. To characterize different kind of solutions, so there are different ways how to do it. We used a Lyapunov exponent approach. So I will briefly explain you what does it mean. So if we have dynamical system in the form of differential equations, we're able to work in the phase space. So in the phase space, the state of which current state of the system will be represented by point. As time involved, time grows, this point will move, creating a trajectory. And Lyapunov exponent characterize the stability of this trajectory. Essentially, it means if you have a limit set as a solution if we have the stationary trajectory in our system and introduce small perturbation to this transition among certain direction in the phase space, and we'll check how this perturbation evolves with the time. We'll probably find our situation when along some direction it grows, and along some directions become unperturbed, along another directions it shrinks. And Lyapunov exponents indeed characterize whether the trajectory which is perturbed in certain direction grows, deviate from the initial trajectory, or converge to the initial trajectories. And in fact, it means it's characterized exponent of this convergence or divergence, and sign of this exponent gives us information about what they call Lyapunov stability. So for the fixed point or equilibrium, when state does not change in time, the all Lyapunov exponent is going to be negative. For periodic solution, the largest Lyapunov exponent is going to be 0. For quasi-periodic solution, when we have two frequency competing, that's going to be two or more largest Lyapunov exponents being 0. And for chaos, finally, one or more Lyapunov exponents is going to be positive, and at least one Lyapunov exponent is going to be 0. So the signature of those Lyapunov exponents allows us to classify the solutions of our system. And this is kind of summary what happens first for two systems. And in fact, in this work, which has inspired us, it was predicted that such a system may demonstrate periodic solution. However, the more fine analysis, more close analysis of the system, in fact, shows us that we have much more complicated dynamical picture, even in such a simple system, having only 2 Rydberg atoms. And this is a diagram presenting the map of regimes. So we have here transition to chaos. There are some bifurcation line, red, which corresponds to certain stability, pitchfork bifurcation, Hopf bifurcation. Then we have a cascade of period doubling, which leads us to the chaos. So even two Rydberg atoms are able to demonstrate chaos here. And this is also confirmed by calculations of Lyapunov exponent. If we consider this in terms of slice of this bifurcation diagram, we can see that area where we have a chaos. In this area, we have a positive Lyapunov exponent. And the area where we have periodic oscillations, here periodic oscillations appear, the largest Lyapunov exponent is 0. So in fact, even two systems can demonstrate quite complicated behavior. But we started then analyze what happens if we put more and more atoms in our system, in our ring system. And as I said previously, it's possible to do if we use, for example, holographic methods for creation Rydberg networks. And this is a bifurcation diagram or map of regimes, to be precise, for 5 Rydberg elements. And here we have an area where we have no oscillations. These oscillations may have a different physical meaning. I don't touch it here yet in this particular talk. But what is interesting, we have periodic oscillations, quasi-periodic oscillations, chaos, and even hyperchaos. Hyperchaos, this is a chaos when we have 2 or more positive Lyapunov exponent in the spectrum of Lyapunov exponents. And essentially, it means that there are at least 2 characteristic directions among which the trajectory diverge. And that's create additional level of the randomness in the system. Here we investigated in more details how the transition to the chaos and hyperchaos occurs. This is a slice along this diagram, and we see that first the Lyapunov exponent become positive on this value, and essentially it's associated with the appearance of the chaos, and mechanism for appearance of this chaos is again period doubling. But then on certain level we have appearance of the hyperchaos, where the second Lyapunov exponent become positive. Now we have 2 positive Lyapunov exponents which are characterizing the stability of our dynamical regimes. Later on we'll have windows of periodicity, and then chaos dies. First again demonstrating periodic oscillations, and then gone to the steady state or equilibrium point. So it was quite interesting finding, because in the Rydberg systems, for the first time, we will find something more difficult, just simple chaos. And to some extent, it might be called quantum hyperchaos with some caution. And this is quite interesting dynamical observation. And this is how different dynamical regimes looks on the spatial temporal plot. This is a number of the qubits, and the gradient here shows the value of the population inversion variable. And you see, and periodic is a quite ordered. In quasi-periodicity, we have second time scales, which is uncommensurate with the first one. In chaotic can become a little bit disorder, and hyperchaotic demonstrate even more disorder in the system. Definitely, once we found out hyperchaos, and this hyperchaos is associated with adding the Rydberg atoms in the chain, we started to investigate what happens if we add even more elements there. So we found out that Lyapunov exponent grows in the time, linearly. And this is how look the spatial temporal behavior of 100 atom chain. And this is really looks like a very noisy picture. And this is indeed confirmed by calculations of the spectra. And this is how spectra change as we increase number of atoms in the system. And for quite big number of atoms, say around 10, maybe 12, the spectrum become really looks like a spectrum of noise in certain solid state system. For example, this mimic pretty much the hot electron noise in semiconductors, which is a result of thermalization. So to some extent, our dynamical phenomena, which are associated with onset of hyperchaos, might be considered, if you're not prepared, as a thermalization. And this contradiction of each other, because thermalizations means closeness to equilibrium. We considering system far from equilibrium. For example, if you an experiment measuring spectra like that, it's very tempting. Almost 90% experimentalists will tell you that this is a noise in the system. However, this is not a noise, this is dynamical regime. And what is a dynamical regime good for? Dynamics might be controlled efficiently with some luck. And this was exactly what we tried to do. We modulated the intensity of the laser light, which means the modulations of the Rabi frequency. And we're able to indeed bring the highly erratic behavior to the periodic one. So in fact, realizing control of very developed hyperchaos in the Rydberg system. And this is how it looks in the XT plot and a special temporal plot. This is without control, this is control, brings regularity into the system. This is my last results, and now let me to conclude. First of all, I would like to think I convinced you that Rydberg system is quite interesting playground. It's not only interesting from classical physics and quantum physics point of view, it's also interesting from nonlinear dynamics point of view, or better to say, from point of view physics far from equilibrium. Interesting phenomenon we observed is onset of chaos and hyperchaos, and even more interesting that the complexity of hyperchaos grows with number of atoms added onto the chain. That regimes, surprisingly, because not so many reports that hyperchaos might be controlled efficiently, but for our system, we are lucky to find out a way to control hyperchaos, turning into the regular periodic oscillations. Two open questions, three big open questions are left here. First of all those findings still needs experimental confirmation. Second thing, as I said, in this particular consideration, we neglected entanglement, but entanglement at the moment is one of the things under very rigorous studies, because the implication of physical phenomena of entanglement not quite clear in many cases. And next thing would be to consider what happens if we add entanglement of the system. And another thing is what is the connection between classical Lyapunov exponent and quantum correlators? So in fact, it recently was shown that the largest Lyapunov exponent corresponds to the rate of out of time order correlator. To certain systems, one-to-one correspondence. But it's still unclear what does it mean hyperchaos and such a thing. we started some simulations with taking down entanglement and got some promising results. In fact, we found out some regular decaying, quasi-periodic decaying, some chaotic decaying, which is again changed by quasi-periodic decaying. The situation mimics what we observed in the system without entanglement. However, it's only in the beginning of this route, and more research is needed in this direction. Thank you for your attention.
Thank you, Alexander, for such excellent lecture. We have time for a few questions. Any questions? Well, I have one. Does hyperchaos in such system have a strong impact in some application, for example, for quantum computing or something like that?
Yeah, thank you. Indeed, assuming if this is found in an experiment, that may have quite interesting implication. One of the things which is needed even in quantum computing is a random number generator.
Okay.
So this is producing a way to have very reliable random number generator, not only in terms of its quantum origin, but also in terms of its chaoticity. Another thing is probably provides a new view on thermalization, because it shows that sometimes what looks like thermalization might be not thermalization. It might be a result of complex dynamics caused by coupling between the interacting coherent systems, quantum coherent systems. And Hamiltonian we used in our research are generic. They might be applied as to spin system, they might be applied to superconducting qubit systems. And in fact, that phenomenon might be expected in some other quantum coherent systems.